Let's think about where our power comes from. The first law of thermodynamics says that energy can neither be created nor destroyed. It can only change from one kind of energy to another kind of energy. So when we are generating power, we are converting mechanical energy to electrical energy. And all power plants do this. There's one exception. Solar panels use a different process. They use the photoelectric principle. But other than that, every single power plant does the same thing. It converts mechanical energy to electrical energy. And that mechanical energy could come from a wind turbine or a steam turbine where the steam got heated by coal, or it could come from a diesel engine or from water behind a dam. Here in the Pacific Northwest, where most of our power is hydroelectric, the mechanical energy comes from water falling, and that turns a turbine. If you're out in a remote area, you might use gensets. A genset is short for generator set, and that is a usually diesel engine attached to a generator. But it could even be a little hand crank thing. Anything that provides mechanical energy can be turned into electricity. Here in the Northwest, up on the Columbia River especially, we have these hydroelectric dams, and the dam makes water build up behind it, and the deeper the water gets, the greater the pressure, and the pressure pushes the water through this intake gate, through this tube. It comes down to a turbine that has fins on it and spins that turbine fast, and that spins this generator, and that generates voltage and current. Here's a shot of those generators at Bonneville Dam and a piece being installed. Here's a shot of a similar flank of generators at Hoover Dam. And it might have occurred to you that generators and motors look awfully similar, and in fact they are awfully similar. They both have magnets and coils of wire, and they both change one kind of energy to the other kind of energy. If you hook them up one direction, you've got a generator, which takes the mechanical energy and turns it into electrical energy. If you hook it up the other direction, you've got a motor where electrical energy comes in and gets transformed into mechanical energy. And all of this happens through a principle called inductance. I don't know if you happened to be in a school when you were in grade school where they did this thing where they took a nail and they wrapped copper wire around it or something like that. They made big loops and then they moved a magnet back and forth. Some of us did and some of us didn't. But here's an illustration of that principle. So here are copper wires and a magnet going back and forth through the wires. And as the magnet goes through there, it changes the magnetic field, of course, and that causes voltage and therefore current in this wire. And it turns out that the closer the magnet is to the wire, the stronger the voltage. As this generator turns, the amount of voltage and thus current changes. So this is 4 positions of this rotor turning inside a magnet. So there's a north pole and a south pole. So in this first position, where the rotor is straight up and down, that wire is close to the magnet, and so the voltage is bigger. Then it keeps rotating clockwise, and now in its flat position, those wires are farthest from the magnet, so the voltage has come down to 0. Now in the third position, that rotor keeps rotating, and now the wire is down close to the south pole magnet, and so the voltage is big again, but now it's on the other side, it's gone the other direction. And now the rotor rotates back around, it's flat again, and now the voltage has come back to zero. That voltage changes in amount and changes in direction. And so we call the power that's generated from these things alternating current. It's actually alternating voltage and alternating current, but you are probably accustomed to hearing the term AC for alternating current. And if you were to graph this current in your wire, you would have a sine wave. Isn't that cool? And the reason for that is because generators turn in circles, and a sine wave is a graph of something as it turns in a circle. And you can make graphs of all kinds of things out there in the world that are turning in circles. In math class, in the natural world, in electricity, you are going to find sine waves all over the place. And they are graphs of things turning in circles. How fast does that happen? Well, in the US, our power plants have all synchronized. They've all agreed that they are going to have their generators turn, make one full revolution 60 times per second, which is pretty darn fast. So we call that frequency, the number of these waves per second, and frequency is measured in hertz, abbreviated Hz. So in the US as well as Western Canada, our frequency is 60 hertz. In most of the rest of the world, they have chosen a frequency of 50 hertz. So that's okay, it works fine. It's kind of interesting to know that if you, and I have done this, if you take a motor that's rated to run at 60 cycles, because it was made for the US or Western Canada, let's say you've got an 1800 RPM motor, 1800 revolutions per minute, that motor is going to turn when it's plugged in the US. And if you take it to some place like I sent one to South America where the power was 50 hertz, that motor turned 1500 RPMs. It was 5/6 as fast, and that is what you call a D-rated motor. You just have to know that and account for what speed the thing's going to turn. But all these frequencies are equally fine. Those generators have 3 arms. So the first arm spins around in a circle and it generates a sine wave. Oops. Then the second arm comes along in a circle and it generates a sine wave. And then the third arm spins around and it generates a sine wave. But they're all offset a little bit because these arms are taking turns spinning around in a circle. That is why we have what is called 3-phase power. So one phase comes in on each of 3 wires that come to your building. And if you're wiring a house, you're probably going to tap into just one of the wires. You're going to use single-phase alternating current. If you're wiring, let's say, an industrial plant, you are probably going to tap into all 3 wires that are coming from outside. You're going to have 3-phase power, and you'll use that to run your big motors, your industrial style lighting. The lighting at in parts of the LCC campus are 3-phase. Last slide. The fact that we have 3-phase power gives our power distribution systems one of their most distinctive features. Just about everything comes in 3s. So these are all pictures that I took out there wandering around. Here's a transmission tower. I think light coming from Bonneville anyway. Notice that on each side there are 3 arms with 3 sets of wires. Then here's a smaller set of wires with a pole next to the street, 3 wires going along the street, 3 wires coming from there to some kind of building. This one here, I think this might be 13th Street. This is near the fairgrounds. These are slightly bigger poles with wires coming from the substation, and notice 3 arms, 3 wires on each side. This one, I think I took this near Eugene Hardware somewhere in South Eugene, and here are 3 wires coming in, 3 transformers. Here's another pole, 3 wires, 3 transformers. So everything comes in threes. And next time we'll start looking at how the power that got generated at the Bonneville plant or wherever, how that power gets distributed. And next time we'll look at some large-scale power distribution, and then the following day we'll look at the smaller scale distribution like you might find bringing power into your house.